In this second part of our discussion on subsequences, we will prove certain results about what are called the cluster points of a sequence, and we will also define what is the meaning of limit inferior and limit superior of a bounded sequence, and give a characterization of these two numbers. So first of all, suppose you are given any sequence of real numbers, then a real number x is called a subsequential limit or cluster point of xn if it is the limit of a convergent subsequence of xn. So this phrase subsequential limit actually describes clearly what you mean by the real number x to be a subsequential limit, precisely that there should be a subsequence of xn which is convergent and which converges to this number x. We also call it a cluster point for a very special reason, that clustering means gathering around. So the number x is such that the terms of the sequence are gathered around little x in roughly speaking. So precisely speaking, what it means is that any neighborhood of x would contain infinitely many terms of the sequence xn. So in that sense, it is the cluster point of the sequence xn. So this is our first result, and you notice that when I defined a subsequential limit or cluster point, then I did not mention whether it was a bounded sequence or not, but all the results which we do in this particular lecture will be for bounded sequences. What happens when we are looking at an unbounded sequence, we will discuss later in another lecture. Okay, so suppose you are given a bounded sequence xn, then you are guaranteed by Bolzano-Weierstrass theorem that there is at least one convergent subsequence of this sequence, and hence there is at least one cluster point of the sequence xn, right? Cluster point just means that there should be a subsequence of xn which is convergent and which converges to x. Okay, so there is if you look at bounded sequences, there it does have cluster points, and the necessary and sufficient condition for a real number to be a cluster point of xn is that any neighborhood of x should contain infinitely many terms of the sequence. So let us see how to prove this. First of all, let us assume that x is a cluster point of xn. Then to show the condition which we have here, what we do is we show that it is true for any epsilon neighborhood of x, and that is sufficient, as we know, because any neighborhood will contain an epsilon neighborhood of x for some epsilon. So for that purpose, what we do is we choose some epsilon greater than 0. Now we use the fact that x is a cluster point of xn means that there is at least one subsequence xnk of xn which will converge to x. As we have seen in the previous lecture, there can be infinitely many subsequences which converge to x, right? Once you have a convergent subsequence, its limit is unique, but this subsequential limit could be the limit of many subsequences, right? We discussed this in the last lecture. So choose one such subsequence, call it xnk, where varying over k, so that limit k tending to infinity xnk is equal to x. So what is the meaning of this particular mathematical expression? We just write it down, that for this particular epsilon, there will be a positive integer k, capital K, so that xnk minus x modulus of that is less than epsilon for all little k greater than equal to capital K. So what does that mean? That means that if you look at the open interval x minus epsilon to x plus epsilon, it will contain all the terms x and k, x and little k, where k is greater than equal to capital K. So such terms are obviously infinitely many terms of the given subsequence. It is after the capital Kth term, and hence of the original sequence, because after all the subsequent consists of terms which are taken from the original sequence. So this means that the epsilon neighborhood of X will contain infinitely many terms of the given sequence, and this is true for any epsilon greater than 0, and hence at least if you have X as a cluster point of Xn, then this condition is true. So that means that this is a sufficient condition, that and now we show that it is also necessary, that is if any neighborhood of X contains infinitely many terms of the sequence Xn, then uh, X has to be a cluster point. So what we will do is we will show a way to construct a subsequence. So there are several choices involved. Let us see. So we are given that any neighborhood of the real number X contains infinitely many terms of the sequence. So first of all, you look at the one neighborhood of X, that is open interval X minus 1 to X plus 1, and look at the set capital S, which consists of all positive integers, so that Xn lies in that open neighborhood, one neighborhood of X, that is mod Xn minus X is less than 1. So by our condition, capital S is going to be actually an infinite set, so it is non-empty, because there are infinitely many terms of the sequence, so that uh, their distance from X is less than 1. Okay, so this is a non-empty subset of the set of natural numbers, so it has a least element by well ordering property. So if n1 is the least element of capital S, then by our choice, we do have that modulus of xn1 minus x is less than 1. So what are we going to do is, so this xn1 is going to be the first term of the subsequence which we are trying to find, which will converge to X. So at the second stage, what you do, I will tell you the general case in a few moments. What you do is that now you have got N1, so you again construct such a set uh, of all positive integers such that the distance between xn minus x, distance between xn and x, that is modulus of xn minus x, is less than half, and you also require that n is greater than n1. Okay, so suppose you have this for less than half, and you are putting another condition here that n is greater than n1. So let us see, the half neighborhood of X will contain infinitely many terms of the sequence. So, and how many terms are there of the sequence till the n1th term? There are exactly n1 terms, so that there are only finitely many. So there will be many terms of the sequence after the n1th term, whose distance from X will be less than half, right? By our given hypothesis. So therefore, if you put in that condition that n is greater than n1 and mod xn minus x is less than half, that will also be a non-empty set. And it is a subset again of of natural numbers, set of positive integers. So by well ordering property, it will have a least element n2. Now what will n2 satisfy? N2 will satisfy that n2 is greater than n1, as well as modulus of xn2 minus x is less than half, right? So we just go on doing this. So that is our induction step, that suppose you have chosen n1, n2, nr positive integers, so that now you understand how we are saying this. N1 is less than n2 is less than etc less than nr, and the modulus of xnj minus x is less than 1 by j for all j is equal to 1 to r. So suppose you have done till this step. If you consider the set of all positive integers so that n is greater than nr and modulus of xn minus x is less than 1 by r plus 1, this set I'm calling T, for example, the just for convenience sake, then what is the meaning of this? You are looking at the 1 by r plus 1 by r plus 1 neighborhood of x. That is, you are looking at the open interval x minus 1 by r plus 1 to x plus 1 by r plus 1. So by our given hypothesis, it contains infinitely many terms of the sequence, right? And till the nrth term of the sequence, there are only finitely many terms of the sequence. So therefore, there will be many terms of the sequence after the nrth term, so that they lie in the 1 by r plus 1 neighborhood of x. Hence, capital T is non-empty, and it is obviously the a subset of the set of positive integers. So again, by well ordering property, it will have a least element. So suppose nr plus 1 is the least element of T. Then by your choice, what do you get? You get that nr plus 1 is greater than nr, and the distance between xnr plus 1 and x, that is mod of xnr plus 1 minus x, is going to be less than 1 by r plus 1, right? So this tells you that by induction you can actually get a subsequence now, because n1 is less than n2 is less than n3 and so on. So this xnk is forming a subsequence of the original sequence. Not only that, it satisfies the property that mod of xnk minus x is less than 1 by k for all positive integers k, right? That is the way you have chosen these numbers. And obviously there is a 0 less than or equal to on this side. So let us just repeat this reasoning once again, so that it becomes clear that as k tends to infinity, 1 by k goes to 0, and 0 is a constant sequence, right, dependent on k, if you like, in this particular case. So that is going to 0. So by sandwich theorem, limit k tending to infinity, mod of x and k minus x is going to be equal to 0, right? This is a null sequence, this is a null sequence, this guy is sandwiched in between them, so that is also null sequence. So that implies that limit k tending to infinity, x and k minus x is equal to 0. Since mod of x and k minus x, that gives you a null sequence, so x and k minus x also gives you a null sequence, but that necessarily means that limit k tending to infinity, x and k is equal to x. So we don't write those many steps every time, but this is the reasoning behind it. So what have you got? You have got that if the condition is satisfied, then x will be a cluster point of the given sequence, meaning that there will be a subsequence of the given sequence which will be convergent and which will converge to x. Excuse me. So this result immediately gives you a condition on the set of all cluster points of a bounded sequence. As I said, we will only discuss bounded sequences in this lecture. So suppose xn is a bounded sequence, and let us denote the set of all cluster points of the sequence xn by capital E. Then the first thing which we observe is that capital E is closed in R. So how will we show that? The way we show a set is closed is that we take a limit point of the set and show that it has to be an element of the set. So suppose x is a limit point of E. Then if you take any epsilon greater than 0, then there will be a y belonging to E dependent on the epsilon, so that mod of x minus y is less than epsilon by 2. Why will you get this? Because if x is the limit point of the set E, which is non-empty now, right? Because xn is a bounded sequence, so Bolzano-Weierstrass theorem is guaranteeing that capital E is non-empty. There is at least one convergent subsequence of xn, so there is at least one cluster point of the sequence xn. Hence, capital E has to have at least one element. That means it is non-empty, right? So if you have a limit point of such a set, then any neighborhood of uh, the limit point will contain infinitely many points of the set. We had proved this. So in particular, if you look at epsilon by 2 neighborhood of X that will also contain a point of capital E. And that is obviously dependent on epsilon. I stressed it here for a reason, you will see. So mod X minus Y is less than epsilon by 2. You will get such a Y in capital E. Now Y is in capital E means what? Y is a cluster point. So Y is a cluster point means that there is a subsequence of the sequence xn, say xn k, so that limit n k tending to infinity xn k is equal to Y, right? So what does that mean? That for this given epsilon, so depending on this epsilon you had chosen Y, and you keep this epsilon static for the rest of the argument also. So for this epsilon you will be able to get a positive integer capital K, such that for all little k greater than equal to capital K, mod of xn k minus Y is less than epsilon by 2. So now you see where you are going. So use triangle inequality. What do you get? You get that for all little k greater than equal to capital K, mod of xn k minus x is going to be less than epsilon, because it is equal to mod xn minus y minus x minus y. No problems. These y's are just added and subtracted here, and that is less than or equal to these two numbers by triangle inequality, and each of them is less than epsilon by 2 if little k is greater than equal to capital K. This one is less than epsilon by 2 is not dependent on capital K, but this one is dependent. So what have you got? That if you look at the epsilon neighborhood of X, then that will contain infinitely many terms of the original sequence, right? And therefore, by our previous proposition, the X is going to be a cluster point of the given sequence. So there, what have you shown? That if you take a limit point of E, then it has to belong to E. Therefore, E is closed. Why I stressed this fact that why this little y which you get is dependent on epsilon and so on, it almost looks like you are getting a condition that x and k is converging to x, but actually you are not. That is what I want to stress. Given the epsilon, you had chosen y dependent on epsilon, which will be in a neighborhood of x. Given this y, you will get a subsequence which will converge to y, and therefore infinitely many terms of this subsequence will lie in the epsilon neighborhood of x. But if you change your epsilon, then the y which you get may be different. I hope you understand. So if you change your epsilon, then the y which you get is going to be different, is most probably a different number, and therefore the subsequence which you choose, which converges to that different number, will be a different subsequence. So if you change your epsilon, the infinitely many terms of the original sequence which will lie in that changed neighborhood of X will not be from this subsequence necessarily. So it is not as if this guy is going to converge to X. What is happening is that whatever epsilon you take, you will get infinitely many terms completely dependent on epsilon here of the original sequence, which will lie in that epsilon neighborhood of X. So therefore, it will be a cluster point of E. That is all you are saying, and hence E is closed. Okay. Next result, which is more important right now for us, but even that was interesting, is that if you have a bounded sequence, and if you look at capital E, which is the set of all cluster points of Xn, then capital E is going to be a bounded subset of R. So how are you going to prove this? We do it by contradiction. Okay, so first of all, capital E is non-empty. We know that, right? Because Xn is a bounded sequence, and hence Bolzano-Weierstrass theorem guarantees that capital E is non-empty. Now suppose that E is an unbounded set. So then I'm not saying unbounded above or below or whatever. We are just saying suppose it is an unbounded set. It may be unbounded above or unbounded below. We don't care about that so specifically. Okay, at least this much is true, that if you take any positive number capital M, then you will be able to get a x, which is a element of E, so that modulus of x is greater than M, right? E is unbounded means you will not be able to make it a subset of any closed interval minus M to M, right? It is not possible. There will be no bound. So for every closed interval minus M to M, you will be able to get a point of capital E, which will be outside this interval. So it may be that it is greater than M, it may be that it is less than minus M. So if it is greater than capital M, what does that mean? That if you look at this open interval capital M to infinity, this is a neighborhood of X. So since X is a cluster point of the original sequence, there will be infinitely many xn in the open interval M to infinity. And if x is less than minus M, then this means that if you look at the open interval minus infinity to minus M, that is a neighborhood of x, right? And therefore this interval will contain infinitely many terms of the sequence. So whatever happens, for keep changing your M, so any such open interval will either keep on having infinitely many terms of the sequence, or any such interval will keep on having infinitely many terms of the sequence, right? So what is going to happen is dependent on whether E is unbounded above or unbounded below. I have just clubbed the proof together so that we don't have to say too many things, but I hope you understand. So if you keep on doing that, it means what? It means that your sequence xn itself cannot be bounded, because whatever m you take, it either in the open interval m to infinity there will be infinitely many xn's in terms of the sequence, so therefore they will all be greater than m at least, or there will be infinitely many terms of the sequence which are less than minus m, so they will be less than they are not bounded by minus m, that is to say, right? And keep changing this m, there you will always get such a uh, thing that there will be infinite many xn's in either this or this. So your original sequence cannot be bounded if E is unbounded. So therefore it is contradicting that fact, and hence whatever we said after if possible is a false statement. So therefore the set of all cluster points of a bounded sequence is actually a bounded set. Okay, so this is a very useful observation, which tells you that if you look at the collection of all cluster points of a bounded sequence, then and I'm calling it capital E, then it will have a supremum as well as an infimum, because it is bounded now, right? So supremum E will exist, infimum E will also exist. Supremum E is what is called the limit superior or upper limit of xn, and of the original sequence xn, and it is denoted by either limsup xn. Many people write an n here, but that is not necessary. That is quite obvious what else is changing here. So if you like, you can write down an n here, or you may ignore it, or it is written as limit, and there is a, we call it upper limit, so that we just put a overline over it and say this is lim sup of xn, right? So this is also a notation. Again, you can write an n like if you like, and you can ignore the n because if you don't like cumbersome notation. Similarly, E has an infimum, and that infimum is called the limit inferior or lower limit of the sequence xn, and it is denoted by either liminf xn or by an underlining of the limit like this. So lim underlined, so this means lower limit xn. Again, you can put a n here if you feel comfortable, and you can ignore it if it is okay with you. Okay, So let us look at an example which will tell us, and this example we will do in great details so that we understand how we are going to tackle this particular problem of what? Of finding the limit superior and the limit inferior of a given bounded sequence. So suppose my sequence xn is equal, given by, the nth term is given by minus 1 to the power n plus sine n pi by 4 for every positive integer n. Okay. So first thing which we will observe is that this is going to be a bounded sequence. Why is it a bounded sequence? We just look at the modulus of xn, then use triangle inequality. What does it become? Mod of minus 1 to the power n plus mod of sine n pi by 4. So mod xn is going to be less than or equal to this. And this is what? This is less than or equal to 1. This is actually equal to 1. And mod of sine n pi by 4 is less than or equal to 1, because sine function takes values between minus 1 and 1. So mod xn is going to be less than or equal to 2 for all positive integers n, and hence xn is a bounded sequence. So what do you know? You know by your Bolzano-Weierstrass that limsup xn and liminf xn exist, right? Because that set of all cluster points is non-empty and it is bounded, we have shown. Therefore this will exist, and this is more or less going to be our standard notation. So I have introduced it here, that whenever I'm talking about limsup xn, it takes lots of time to write this, right? So it will be useful if we use a smaller notation for it, and during the course of our lecture we will use mu for limsup and lambda for liminf generally. Okay. And the reason I have chosen mu and lambda is very simple. In in the books you will consult, especially written by Bengali authors, mu and lambda has been a standard choice. So we do the same thing so that there is no confusion when you compare it with the books. Okay, so enough of that. So now we want to find out what is mu and what is lambda. So the best way to do this is look at your sequence. Here what is happening, there are two parts, right? There is a minus 1 to the power n which is taking values 1 and minus 1, and in fact sine n pi by 4 is also going to take only finitely many values. How can you be so assured about it? Is the fact that sine is a periodic function, first of all, and if you take any positive integer, then there is a 4 here in the denominator. See, so this 4 is going to determine what are your choices going to be, first of all. So take any positive integer, it looks like either 4k or 4k plus 1 or 4k plus 2 or 4k plus 3. That is, if you divide a positive integer by 4, then you will have uh, a multiple of 4 plus some remainder. And that remainder, what can it be? It can be either 0 or 1 or 2 or 3, because you're dividing by 4, right? So therefore, dependent on that, you will get distinct values of sine, and therefore you will get distinctly many, finitely many values of xn. And that helps you determine what your set of cluster points is going to be. So let us observe. Let us look at terms of the form, uh, that is positive integers of the form 4k, right? So where k is in n, so 4, 8, 12 and so on. So what is sine 4k pi by 4? That is just sine k pi, right? 4 cancels out and therefore it is going to be 0, right? Look at what happens to sine 4k plus 1 pi by 4. I said that if you take an integer, here there was an n sitting, right? So that n will have only these 4 forms. So we do check these 4 forms individually. So what is sine 4k plus 1 pi by 4? Now I am taking k to be either a positive integer or 0, because I want 1, 2, 3, 4 also, right? 4 is included here because if you take k equal to 1, then you'll get 4. But for getting 1, 2 and 3, I need to take k to be 0 also. So I'm including that. So what is this going to be? Again, you use the same type of uh, calculation which you used here. Just divide by 4. So you get sine k pi plus pi by 4. Now use the addition formula. What do you get? Sine k pi cos pi by 4. That will become 0 because sine k pi is 0, plus cos k pi sine pi by 4. So what is cos k pi? That is equal to minus 1 to the power k, and sine pi by 4 is 1 by root 2. So sine 4k plus 1 pi by 4 is going to be equal to minus 1 to the power k divided by root 2. So it is not taking only one value, see. It is actually taking two distinct values dependent on whether k is even or odd. If k is even, then the value is going to be 1 by root 2. And if k is odd, then the value is going to be minus 1 by root 2. Right? Okay. So now the next one which we want is to look at sine 4k plus 2 pi by 4. Then what will this be? This is just sine k pi. Just do the simple calculation plus pi by 2. Right? Now there is a 2 pi. So 2 pi by 4 that becomes pi by 2. Again use the addition formula. Then you will get sine k pi cos pi by 2, which will be 0 because sine k pi is 0, plus cos k pi sine pi by 2. And what is cos k pi sine pi by 2? Sine pi by 2 is 1. So this is just equal to minus 1 to the power k. So again, it is going to take two values, minus 1 and 1, dependent on whether k is odd or even. Right? Similarly, for sine 4k plus 3 pi by 4, notice what here I've done a simple trick. You could have just written 3 pi by 4 if you remember the value of that. But if you like, you can just write it like this. What I have done is instead of writing 4k plus 3, I'm writing it as 4k plus 4 minus 1. So 4k plus 4 is 4 into k plus 1 minus 1 here. So you get sine of k plus 1 pi minus pi by 4, right? And again you use the subtraction formula, if you like, of sine. So it becomes sine k plus 1 pi cos pi by 4, which is 0, minus cos k plus 1 pi sine pi by 4. Now what is cos k plus 1 pi? That is equal to minus 1 to the power k plus 1. And there is a minus here at the beginning of this term. So total, what do you get? Minus 1 to the power k plus 2. But minus 1 to the power k plus 2 is equal to minus 1 to the power k. So you just get this. And sine pi by 4 is 1 by root 2. So the values it will take is again going to be plus 1 by root 2 or minus 1 by root 2, dependent on whether k is even or odd. So for sine, we have calculated all these distinct values. So we see that you can actually, so this is partitioning your sequence, right? Your sequence is the second part. You have two sums, two terms in this sequence expression or nth term of the sequence. One is minus 1 to the power n and the other is sine n pi by 4. Now sine n pi by 4 is telling you that you can actually write down the terms of the sequence in it will take four different values dependent on k roughly, and then if you look at it closely, then there are actually uh, two values here and one value, two value here. So 4 plus 1, 5. So there are total 5 values because this is repeated, right? So there are total 5 values which sine n pi by 4 is taking, and dependent on the value of n. And minus 1 to the power n is taking two values. One is minus 1 and the other is 1, dependent again on the value of n. So what is your xn going to look like? Let us see. If you take n is equal to 4k, then n is even. So minus 1 to the power n becomes 1. And your sine 4k pi by 4 was 0. So minus 1 plus 0, it becomes 1. If n is 4k plus 1 or 4k plus 3, when k is either a positive integer or 0, then it is odd, right? So since it is odd, minus 1 to the power n is just minus 1 plus the sin n pi by 4 part will give you minus 1 to the power k by root 2, right? And when n is equal to 4k plus 2, again n is an even number, so minus 1 to the power n becomes 1, and this part is, we have calculated sin n pi by 4 part is minus 1 to the power k, so it becomes this, right? So how many values are there which xn is taking dependent on which term you take? It is 1 here, 2 values here, right? And 2 values here. So there are total 5 values. So you notice that if you look at limit k tending to infinity x 4k, that is going to be equal to 1. So if you just look at the 4kth terms of the original sequence, that is a convergent sequence. It is actually a constant sequence converging to 1, constant sequence taking the values 1, so therefore it converges to 1. Similarly, if you put here k is equal to some 2m, right? So dependent on whether k is even or odd, the value will change. So suppose first we put 2m. So how much will this become? It will become 8m plus 1. So look at the subsequence which consists of 8m plus 1th terms of the original sequence. That is again a constant sequence taking the value minus 1 plus 1 by root 2, because if you take 8m here, then this k is actually 2m, so it is becoming 1. So you get a subsequence of the original sequence, which is a constant sequence taking the value minus 1 plus 1 by root 2. So it is going to converge to minus 1 plus 1 by root 2, justified. So you get 1 as a cluster point, you also get minus 1 plus 1 by root 2. Similarly, if you take k to be odd here, so suppose 2m plus 1, then total effect will be what? Let us calculate. 4 into 2m plus 1 is 8m plus 4 plus 1. So that becomes 8m plus 5, right? So if you look at a sequence, a subsequence of the original sequence consisting of 8m plus 5 fifth terms of the sequence, then they are going to form a constant sequence taking the value minus 1 by root 2, right? So therefore minus 1 by root 2 is also a cluster point of the original sequence. Again, do the same type of thing here. If you take k to be even, say suppose twice m, then you get numbers of the form 8m plus 2. So you have a subsequence of the original sequence consisting of the 8m plus 2th terms of the sequence, which is going to be the constant sequence. And what is going to be the value of that constant sequence? It is minus 1 to the power an even number, so it becomes 1 plus 1, so it's going to be 2, right? So 2 is also going to be a cluster point of the given sequence. Similarly, if you take k to be odd, so then it becomes 4 into 2m plus 1 for some m. So that becomes 8m plus 4 plus 2, right? So 8m plus 6. So if you take a subsequence of the original sequence consisting of 8m plus 6th terms of the original sequence, then that is again a constant sequence, and the value is going to be 1 plus minus 1 to the power something odd, so it is going to be 0. So that subsequence converges to 0. Therefore, 0 is also a cluster point of the given sequence. So determining that these 5 numbers are the cluster points of the given sequence, even though it took some time, is straightforward. What I want to tell you now is that it is actually these are the only cluster points. So why is that going to be true? That is going to be true because the way we have these terms, you see that the whole sequence has been partitioned into subsequences which are constant sequences, right? So look at all the 4kth terms that give you one sequence. I have not talked about this, but this is also included here, right? It will give the same values. So I've ignored it. But when you're talking about partition, you have to include this terms also. So any what you're doing is you're looking at all the terms of the sequence. If you look at all the 4kth terms, they are giving you a convergent sequence. If you look at all, so look at all the 4kth term, or all the 4k plus 1th terms, or all the 4k plus 3th terms, or all the 4k plus 2th terms. That comprises of all the terms of the sequence, right? And each individually is going to give you either a convergent subsequence as it is, or if you look at it a little bit more carefully, you actually can extract two convergent subsequence from here, which again form a partition of this 4k plus 1th term, say, for example, right? If you take k to be even and k to be odd, then those terms will form a partition of the 4k plus 1th terms of the given sequence. So essentially, when you want the values which are taken by the given sequence are only these 5 many. That is what I'm trying to say. So therefore, if you want a subsequence which is convergent after a certain term, that subsequence has to be uh, a constant sequence which takes one of these 5 values. That is what I'm trying to say. Your sequence has is taking only finitely many values, and therefore if you want a convergent subsequence of the given sequence after a certain term, the subsequence should be taking one of these finitely many values. It should be constant at that, right? So therefore these are the only cluster points of the given sequence. I hope I have explained it to you properly. We will not bother to write down the proof of this every time we look at an example, right? So I have not bothered to write it here. So because you can see that it is going to take some uh, elaborate argument, and writing that down is slightly boring also for a person who is going through the example. So we just don't bother writing about that, but we understand that what is happening. So now, since this is a finite set, there is absolutely no problem. The supremum of this set is going to be the maximum element, which is 2. Therefore, the limsup of the original sequence is 2. Similarly, the least element of this finite set is minus 1 by root 2, and therefore the liminf of the original sequence is minus 1 by root 2. I hope I have made myself clear. Again, I had planned to talk about the characterization of limsup and liminf also in this lecture, but I think this much is enough for fixed lecture. So I'll stop here, and in the later uh, next lecture we will talk about the characterization and look at some more results, as many as we can. So let us stop here.